This is chapter 8, question 97. It says a fireworks rocket is fired vertically upward at its maximum height of 80 meters. It explodes and breaks into two pieces, with one mass 1.4 kilograms and the other mass 0.28 kilograms. In the explosion, 860 joules of chemical energy is converted to kinetic energy of the two fragments. Question A, what is the speed of each fragment just after the explosion? And B, it is observed that the two fragments hit the ground at the same time. What is the distance between the points on the ground where they land? Assume that the ground is level and air resistance can be ignored. So our question looks like this. You have your firework launches up, then at I think it was 860 meters, it blows up. You have one piece go this way, you have another piece go this way. And we just want to know, see, question A was, what is the speed right here of each segment or fragment, and then what this distance is when they land on the ground. So to start, we can set our 860 joules of chemical energy equal to our kinetic energy equation. So that would be 860 equals the 1/2 mv squared plus m2v2 squared. So that's our kinetic energy equation, and then the amount of chemical energy. So then we need to take our equation for the conservation of momentum, and we're going to put, see if you guys can do it here. All right, it's 0 equals MAV. In this equation, we have all the information for the mass, but we don't have the velocities. We have two variables, so we need to solve this for VB, and then we can have this term, this equation, all in terms of VA. So VB equals, let's see, now I can plug this term into here. So we have all our values that we need for this. Now I can plug them in and solve for VA. The VA comes out to be is VA equals the square root of 2 times 860 over MA times 1 over MA. Yeah. Now we can plug in our values. And when you do that, you come out to 14.3 meters per second for VA. And just a little recap on the values I plugged in. So for MA, that's your larger mass, that's the 1.4 kilogram. Then MB is the 0.28 kilogram mass. So this 14.3 is the speed of the the larger mass, the 1.4 kilogram. Now I can do the same thing for VB. Actually, we use this equation for VB here. So we have MA, we have VA, we have MB. So it's MA, which is the 1.4 times the 14.3 divided by 0.28 for MB. And then VB comes out to be 71.6 meters per second. And that makes sense because if you have the same energy going into both masses, it seems like a smaller one would take off faster. So for part B, now we need to find how far apart they land. Now we can use kinematic equations to solve for how long they're in the air. So we have y minus y naught equals v naught t plus 1 half a is a t squared. Yeah. So on this side, it's up 80 meters in the air. So the difference, will be 80 meters. Initial velocity is 0. That term drops out. 1 half. Acceleration is 9.81. And t squared. Divide by and take the square root of this. Equals your t, which equals 4.04 seconds. So that's how long they are in the air before they hit the ground. Now I can take that time, take your 71.6 times 4.04. So part B, or the mass B, traveled 289.26 meters. And then the 14.3 meters per second times 4.04 seconds gives us 57.8 meters. Now when you combine the two, that's where you come out to 347 meters apart. So this is their speeds. That's how far apart they are when they hit the ground. And that is it for question 97.